So how does a router forward data packets? Well, both hosts and routers maintain forwarding tables. These forwarding tables are simply lists of pairs where the first element of the pair is either a network or a host, and the second element is the next hop. This is the next router we want to forward this packet in order to reach the destination. Often, this list will also contain a default route. This is a route to be used in case the packet wants to go to an address which is not in the list we already have. Inside hosts, these lists are usually very small and they are statically maintained. That is, they are initialized to some usually default route. In routers, these lists are built dynamically by the routing protocols, which are the subject of another talk. And in the Internet core, we can have more than 400,000 entry in such a table, which is really a large number, require a lot of memory that works very fast, so it is a non-negligible part of the cost of a router. When we look at this list, we might have several matches for an IP address, and we're going to use the longest prefix matching algorithm in order to allocate the best match for our IP address, as we'll see in the next slide. So suppose the routing address in my router looks something like this. There's some private IP address that the next hop for it is router 1. Then there's the /13 IP space we looked at that is routed through router 2. Then part of this large address prefix, we have another network that Tel Aviv University /16, which is routed through router 13. And then there's a subnetwork inside Tel Aviv University where it's router 3, route 4, and there are some specific hosts for which there's a different routing. And of course, there's the default route. So if I want to route to a packet to 132.65.201.3, there's only one match for this IP address, apart from the default, of course. So I'm just routing this through the one entry that matches this IP address, and this means I'm going to forward this packet to router 2. However, when I get a packet to 132.66.48.16, there are 3 matches in the table. I can use the upper one, the /13 address prefix. I can use the /16. I can also use the /24. Since the /24 is the longest prefix that matches this packet, I'm going to use this one. So this packet is going to be routed to router number 4. Now the fact that I have multiple matches, possibly I can have multiple matches for a packet, for an IP address, makes algorithm for searching for longest prefix matching fairly complex. Of course, if I want to send a packet to 132.66.48.2, we have now 4 different matches in the table, and I'll take the last one, the lower one, which is the longest one, 32-bit match. What you see here is the way it appears in the RFC, which is the IETF, the Internet Engineering Task Force standard. So it has multiple fields. Each line here in the diagram is a 32-bit word. This is the default way to describe it. So the first 4 bits are the IP version. Right now we discuss IP version 4. So it's always going to have 4 here. Next, there's the header length in 32-bit quantities. This is in words, which means that the header length can be variable, as we'll discuss shortly. Next, there's the total packet length, 16 bits, and this length is in octets or bytes. Finally, there's in this word, there's a type of service field, which we're going to discuss in the next slide. So originally, the type of service field was divided into 3 bits of precedence, 4 bits for type of service, and 1 bit which was default set to 0. The idea of the field was to be able to differentiate between different ways of handling packets in the network. So each packet can belong to some class. However, this standard was changed every so often, and currently the allocation of the type of service field is as follows. There are 6 bits for differentiated service, diffserv, as appeared in RFC 2474, and then the 2 additional bits are for ECN, explicit congestion notification, as appeared in RFC 3168. However, we cannot trust this not to be changed in the future, especially the 6 bits for the diffserv that are defined. As we said, IP can run on any layer 2 protocol. What happens if an IP packet arrives to a router and the next hop medium it needs to travel cannot accept packets that are as large as this one? What IP is doing, it takes the packet and fragments it into smaller fragments and then reassemble them all back to the original IP packet at the receiving host. To do this, it needs these 3 fields in the second word. The identification field is the one that identifies all the fragments to belong to the same packet. The flags indicate whether the fragment is the last or an intermediate segment, and the offset tells what is the offset of this segment from the beginning. The time to live field was originally designed to track the amount of time a packet spent in the network. The idea was that each router is going to decrease from the time to live the time the packet spent queuing in this router. However, this is too hard to be done, and what's happening is that each router is just decreasing the time to live counter by 1. So when you send a packet, an IP packet, you initiate the time to live field to some large enough number, and then when the packet reaches 0, it means that it was traveling too long. For example, if you set the time to live field to 64, it's really unlikely that your packet is going to be traversing such a long route in the network. And what it really indicates, if it reaches 0, that there's some problem with the routing. Maybe there's some routing loop. So the packet is dropped. The protocol field tells IP which protocol the packet that arrives to a host need to be sent to. It can be, for example, TCP or UDP or any other layer 4 protocol. It can also be IP itself in case that what is transmitted here is a fragment of a packet. And as you remember, IP's responsibility is to take all the fragments and reunite them into one packet. And finally, there's a header checksum that makes sure that there are no errors in the header. The next bytes are the source and destination IP addresses for the packet. And finally, there's an option field, which can be variable size. And at the end of this option field, there's padding to words of 32-bit. A few words about the option fields. There are several options. The most common one to be used is source routing. It can be either strict or loose. We can have record route option. There, each supporting router can stamp its IP address in the header, so we can track the route that the packet actually traversed. And there's also a timestamp. The option field is variable in size because we can have multiple options. And also in some cases, like in a record route and timestamp, routers may need to add additional information to the header. As a result, the header size changes. Note that options are optional. That is, that routers do not have to support them, and some options are really supported by only a low percentage of the routers in the internet. And the padding is just filling the packet to the 32 boundaries, because as we see, the header length is counted in 32-bit units. When you put a host in the internet, it needs to have an IP address. One way to do it is to statically assign it an IP address. For example, go to the network operator, ask for an IP address, and then statically insert it into the host. However, this is not very common and it's not convenient. So instead, people using DHCP for a dynamic host configuration protocol. The idea here is that the host broadcasts a DHCP discover message that reaches some DHCP server. The server looks at the request, or at the discovery message, which is a request, and allocate it an IP address. It can also implement all sorts of security measures. For example, checking if the MAC address of the host is a valid MAC address, or if the hosts have the right authority to be active in this network. ICMP is the Internet Control Message Protocol. It is a layer 3 protocol companion to IP, and its purpose is to handle errors and control messages. When there's some problem with an IP packet, it is dropped. But once it is dropped, ICMP is sending an error message back to the source in order to notify it that there was an error. Example errors are host unreachable if IP doesn't know how to reach the host, network unreachable if the entire network cannot be reached or the router doesn't know how to reach it. If IP checksum failed, the packet is again discarded. If the time to leave field reaches 0, that means that it exceeded. If the header is invalid, or if reassembly is failed. There are also control messages. For example, there's a echo ping request which is used by network operators to see what is the round trip time between their location and some destination host. There's also a route redirect message, and echo ping requests can also be timestamped. So we discussed the IP protocol and the IP packet header. We couldn't cover everything in IP. It's a very large topic, but we touched on the most important parts of this protocol.